So this is the 11th session in the subject of digital communications, and we continue our study of baseband modulation. Now remember, in some of our earlier sessions we have already studied three kinds of signaling methods and also three parameters on the basis we can compare these signals. In this session we are going to introduce two more parameters on the basis of which the signaling can be compared, and we'll also introduce one more signaling method. That is what we are going to do. So we'll first quickly revise what we have studied and then list the two more parameters that we are going to study. So we have already talked about the noise performance of the three signaling methods that we have studied. We have talked about the bandwidth requirement. Lesser the bandwidth, better is the signaling method. And we have seen whether clock signal can be extracted from the signal itself. Now the two more parameters that we are going to study now, they are listed like this. So when we plot the power spectral density of the signal, we want to find out whether it contains a lot of low frequency component. Is the PSD zero at zero frequency? Does it have a discrete direct component, discrete DC component? Now if it has a lot of low frequency component, it is not considered good for the reasons we'll study soon. So this is the fourth parameter that we'll study. Then transparency. So we have said that there are certain signaling methods from which the clock can be extracted. Now this clock will have a certain amplitude, and if the amplitude depends on the pattern of the incoming bits, remember it's a information carrying signal, so the pattern of the bits is going to be random. And if the pattern is such that the clock component amplitude goes on reducing, then it's not good. Then we say that the signal is not transparent. So these two we are going to study. So now we have already said that a lot of low frequency component or a discrete DC component is not good. And what is the reason for that? One reason is that repeaters are often used when you have a long transmission line. In between you will find that the amplitude of the signal has become quite low, and it will be necessary to regenerate the signal by using what is called as a regenerative repeater. So it may have an amplifier and so on. But these repeaters are often AC coupled, and since they are AC coupled, and if the signal has lot of DC component, you will find that it will get distorted as it passes through the AC circuit. So we'll see some specific examples of what happens to the signal. Okay, so effect of AC coupling, that is what we want to study. Now consider a polar signaling method, and of course the information carrying signal, as we have said time and again, that it's a random signal. But for the purposes of study right now, let us assume that we have a signal which is consisting of large number of ones first. So how the polar signal will look like? It will look like this. Remember, 1 is coded by a positive pulse. So 1, 1, 1, 1, etc. And this is a half width pulse, which means that the DC component in this signal is going to be V by 2. Now, when this signal passes through an AC coupled circuit, the DC component cannot go through. So what will happen? At the output of the AC coupled circuit, the whole waveform will shift down so that the net DC component is 0. So this at the output with AC coupling, this will become V by 2 is minus V by 2, so that this area is equal to this area and the net DC value is 0. So the whole waveform shifts down. Now at the receiver, when we receive this waveform, and if we try to decode our 1 and 0 directly from this, then you will see that your noise margin gets affected. Here, remember, for polar signaling method, your threshold is 0. So on one side you have V, and the other side you have minus V. So you got full V as the noise margin. But here it has reduced to V by 2. So if we do not do anything to this signal and try to detect our 1 and 0 from this, clearly the noise margin has become half here. So what we can do? So at the receiver, we can use a clamping circuit so that it restores the DC value. So it will shift the whole waveform upward. So you'll get your original polar signal and you will get your noise margin back. However, there are problems in using this clamping circuit. Let us discuss them. So first of all, we have said that if we don't use the clamping circuit at all, then the noise margin now becomes V by 2 rather than V in detection. So solution, we said we use a clamping circuit to restore the DC value, so we get the original noise margin. But this does not completely solve the problem because see, the waveform that we showed, V by 2 minus V by 2, that was a steady state waveform. And whenever the pattern of signal changes, the steady state is not achieved immediately. It takes a certain amount of time. So your peaks, positive peaks and negative peaks will keep on shifting before the steady state is achieved. And because of that, the noise margin will again get affected. So as we said, let me just read it out again. When the data pattern changes, initial transient will cause lower and higher peaks to vary. They don't remain same, they keep on changing before reaching the steady state. This will affect the noise margins. Therefore, it is better to use signaling methods which you do not contain the DC component itself. Not only that, but it does not contain a lot of low frequency component also. Because even if it does not have a discrete DC component, it has a lot of low frequency component that will also be not passed properly through the AC coupling, and you still have this transient problem. So it is better to use a signaling method which contains low frequency components. Okay. Now one more parameter that we wanted to study was transparency. We have already said something about it. Let me give you a example of this. So first of all, note that in certain signals, clock signal can be extracted from the signal. For example, from on-off signaling, in on-off signaling method, you can extract the clock. So consider on-off signaling, it contains clock component. But if a long string of zeros appears, then the amplitude of the clock signal decays. So we say therefore that on-off signaling is not transparent. Okay. So this is one more parameter. So let us quickly look at the table in which we compare the various signals on these 5 parameters. So on-off signaling, polar and bipolar. If you consider the DC component and the low frequency component, there is no null at 0 frequency. Note that what we are talking about here is the power spectral density versus the frequency plot. So at f equal to 0, there is no null. You got some finite value. So this is not good. For polar also, although it does not have a discrete DC component, it has no null at 0 frequency. But bipolar signaling has got a null at 0 frequency. So in that sense, bipolar is better than on-off and polar. What about clock? Can you extract the clock? From on-off signaling you can extract, from polar and bipolar you cannot extract. However, what you can do at the receiver is that for polar signal, as we discussed in our last session, you can use half-wave rectifier in order to convert polar to on-off signaling and then extract the clock. Whereas for bipolar, you can do full wave rectification and then you can extract the clock. What about noise immunity? Noise margins are less here, so noise immunity is poor. In polar, noise margin is good, so noise immunity is good. In bipolar, again, the noise margin is less, so the noise immunity is poor. And we have already studied in the last session that for on-off signaling, the bandwidth required is 2R. For polar also it is 2R. And for bipolar it is R. So from bandwidth efficiency viewpoint, bipolar is a better signal. For transparency, on-off is poor. For polar is good. For bipolar it is poor. So note, for polar it is good because the signal never goes completely zero. It is either a positive pulse or a negative pulse. Therefore, once you extract the clock frequency after half wave rectification, you will find that the signal is going to be transparent. All right. So now, having compared this, what we are going to do is to study one more type of signaling, that is called as a Manchester signaling. Now in Manchester signaling, what is done? If you want to code 1, it is not just coded by a logical level, high or low, not like that. So you have a pulse to code logical 1. So you start with a high value, then around TB by 2, it becomes low and again remains low. So it is this negative edge essentially which denotes the logical 1. And pulse for logical 0 is having a edge in the upward direction. So it starts with 0, jumps to high and then remains high. This is the basic technique of Manchester signaling. So in order to get some feel for this, let us look at some data, a sequence of ones and zeros, and see how the signal will look like. So suppose you have 1. So this shows the time period, that is the bit time. So during bit time, 1 bit is being transmitted. So if 1 is to be transmitted, you have a edge in the negative direction, 1. Next you want to transmit 0. So this remains 0 and then there is an edge in the positive direction and it remains 1. Now the next is 0. So this will come down to 0 first. That is the lower level first, remain lower level, and then there's the upward transition. So that is your 0. So it is the edge that is essentially deciding whether 1 was transmitted or 0 was transmitted. So what can be done is, at the receiver, you can sense the value at this point. Say this is TB, this is TB by 2, this is TB by 4. So at TB by 4 you can sense the value, and then at so this is TB by 4, this TB by 2, this 3 TB by 4, you sense the next value and see whether it has decreased or it has increased, and based on that you can take your decision. All right. What about the various parameters on the basis of which the Manchester signaling can be compared? So it can be shown that it does not contain DC, as you can imagine qualitatively, because for each bit it has a positive component as well as a negative component which is equal and opposite. Therefore you expect null in DC. Can you extract the clock? Yes, you can extract the clocks from this. Noise immunity is good, similar to polar signaling. But the bandwidth in this case is 2R. Transparency is again good, and Manchester signaling, because of these properties, although the bandwidth requirement is somewhat higher, but the noise immunity is good, clock can be extracted, and low frequency DC is null. Because of these, the Manchester signaling was often used in the early versions of the internet. So in this session, we have studied 2 more parameters on the basis of which the signaling methods can be compared, and we have also described what is Manchester signaling and mentioned that this was used in the early versions of Ethernet. And that's all in this session.